Welcome back. We're going to do some more integration by parts today. Last video we introduced this concept and we introduced an equation that helps you break down integrals of products and solve some of them this way. So we introduced this equation here, and it came from the product rule for derivatives. I encourage you to kind of keep writing it down every time you start a problem, and just kind of start to commit it to memory. But essentially, again, what this equation does is it allows you to express the integral of a product in terms of another integral, and if done properly, what we're hoping for is that the integral you have on the right side is a simpler one than you start with, and hopefully it's one where you can now solve it just with a basic integration rule like the power rule, or it might be a simple U substitution again here. But what I'm going to show you today is a couple examples of where, after setting up the integral by parts, the integral that appears on the right side has to be solved again by integration by parts. It's simpler, but it's going to require integration by parts again. Let's see when that might occur here. I've got the function x squared times e to the 3x. Now our guidelines say, and I'm going to write the equation again, integral of u dv is equal to uv minus the integral of v du. And we make this little chart here. I showed you this in the last video, where everything about u and its derivative is on the left side. Everything about v and its derivative is on the right side. And remember, u and dv are parts of the original integrand. And I think the last video kind of pointed out that we probably want to pick the exponential function as dv, and we want to pick x squared as u, simply because its derivative is easy and it's 1 power smaller. Now, if dv is e to the 3x, be careful here. The antiderivative is more than just e to the 3x, because if I were doing this integral just on its own, think about this for a minute. You really want to think of this integral just here as e to the u. I know we're using u a couple different times here, but if this were e to the u, and you would have to write out u equals 3x. du is actually 3 dx, and we would end up putting 1/3 on du. This is really 1/3 e to the u du, and so the antiderivative is 1/3 e to the u here. So if I'm integrating e to the 3x, the antiderivative is 1/3 e to the 3x. So there's a couple instances where you have to watch for that. Okay, and so you'd have to do the similar thing if your dv was like the sine of 2x, then the antiderivative is going to have a 1/2 in it. Okay, but that being said, let's start filling this in. So the original integrand was x squared e to the 3x dx. And now I've got my table filled out correctly, and uv would be x squared times 1/3 e to the 3x. And this time I'm just going to not put the 1/3 in the front quite yet. Minus the integral of v du. Now I am going to put 2x in front of 1/3 e to the 3x dx. So simplifying this is your original u times your original v. And over here, this is v du, although it's backwards. Okay. Now, The reason why I'm writing it backwards at first is because first I want you to notice that the integral I now have is still a product of two functions involving x. One of them is 2x, one of them is 1/3 e to the 3x, and this first part's technically done, so I'm going to write it now 1/3 x squared e to the 3x. But check out this other integral here. This is still a product of two functions, and they both involve x. So I'm looking at this. It's not a way to simplify it other than to put the 2 times 1/3 together. And for this time around, I'm actually not going to do it, just to emphasize something I'm going to get to in a minute. This integral also requires integration by parts. Okay, so I'm going to change colors now because I'm going to make another table in green. And this time, I'm going to look at this integral and reassign u and dv because we're going to do integration by parts again. This time, I'm going to pick the 2x to be the new u and 1/3 e to the 3x to be the dv part, because I can just integrate that similar to the first time around. I've got to make it e to the 3x, and I got to divide by 3 again, so it's now going to be 1/9 e to the 3x. But the derivative of u du is simply going to be 2. Okay, so I am going to write in yellow anything that was already finished from before. 1/3 x squared e to the 3x minus, and now we are going to put in green the result of this integral, also done by parts. It's going to be the new u times the new v, which is going to be 2x times 1/9 e to the 3x. That is minus another integral. It's v times du, so that's going to be 2 and then 1/9 e to the 3x. So now notice this part could be simplified further. This still has to be integrated, but notice now it's now just a constant, which would be like 2/9 times the function e to the 3x. Now that is a basic integral, or at least one that doesn't require integration by parts. And so we're now going to finish the answer here. This is going to be 1/3 x squared e to the 3x. Now I'm going to distribute my minus sign. So minus, and I'm going to combine the constants here to be 2/9, and then I'd have x e to the 3x. Don't forget to distribute the minus sign over here. Now we're going to have a plus, and now I'm going to be thinking of this as 2/9 e to the 3x. That integral doesn't require integration by parts. It's actually just another version of the integral I did on the side the very first time. It's going to be e to the 3x. I got to divide by 3 again, which makes it, it's going to make it 2/27 e to the 3x. And then we are done. So our antiderivative has 3 terms here. And it's because we had to use integration by parts twice. Okay. Now, what I wanted to do in this one example here, and talk about why I did not simplify these integrands as I went down, I want to follow the chain of events here. Notice that in the first round of integration by parts, the integral we had left was the original derivative of u times the antiderivative of dv. And then when I redid this one, I picked 2x, which was the original du. I picked that as u, and I found its derivative again. So in other words, this 2 here is really the second derivative of the original u. Okay, so if you look at the table, I went u is x squared, du is 2x. Then I just recalled that u and then found its derivative here. And if you think about it, we kind of did the reverse with dv. The original dv in the original problem was e to the 3x. Its antiderivative was 1/3 e to the 3x. That became the dv in the second antiderivative, and I integrated it again, and I got 1/9 e to the 3x. And then my last round was I had to just integrate 1/9 e to the 3x. That was already multiplied by 2. I would like to write this integral again and show you just a streamlined approach to get the answer quickly, especially when you're letting the original u be a power function like this. This is really the only time this little shortcut's going to work. Okay, so the original integrand was x squared times e to the 3x dx. Now this time, I'm going to just make a table like this, u and dv here, and my original integral by parts method, I picked u to be x squared, and I picked dv to be e to the 3x. Now, if you remember, in the 3 steps, I kept finding derivatives of x squared, because in the next round, u became 2x. But I'm going to keep finding derivatives here, so the derivative of 2x was 2, and remember, we needed all of those in the way we did this last time. And I'm going to be finding antiderivatives in this column. Okay, so all down here, we're finding derivatives. As we work down this column, we're going to be finding antiderivatives. Remember, the integral of e to the 3x is really 1/3 e to the 3x. And then the integral of that again is 1/9 e to the 3x. And we're actually going to integrate one more time and differentiate one more time. And it's 1/27. Notice we keep dividing by 3. Okay? Now, let's look at our integration by parts formula one more time. And notice the first part of every integral by parts is uv. So if the original u was x squared and the original dv is e to the 3x, then v would be 1/3 e to the 3x. So the first integral by parts, uv, is going to be found by multiplying these together. Okay? But then in the next integral by parts, it required you to reassign the name u and v. So in round 2, this 2x became your u, and 1/9 e to the 3x became v. And so we multiplied these together also. And we would keep doing that, and this one here gets multiplied together also. Okay? So it looks like I'm going to keep doing this until I have one of the factors be 0, because if I kept going, then it wouldn't matter what this is because it's going to be 0, and then I would have to stop. So it looks like if I just keep following the repetition here, multiplying u times v, and in a minute I'm going to ask you to compare this to what we got a minute ago. Now I didn't rearrange these, but I've got x squared times 1/3 e to the 3x. I've got 2x times 1/9 e to the 3x. I've got 2 times 1/27 e to the 3x. That would give you x squared 1/3 x squared e to the 3x. 2/9 x e to the 3x. 2/27 e to the 3x plus c. Now I'm going to go back one page and compare that to what we got a minute ago. And I noticed one small mistake. I was supposed to have a minus sign in the second spot. Okay, so this is actually the correct answer. I have one sign mistake right there. Okay, and the reason that is because every integral by parts has subtraction in it, And so I didn't really make a note of that in my table. So what we do to correct this is, as I make this table, make sure that every other row has a minus sign in it, and then apply it as needed. So x squared times 1/3 e to the 3x has a positive. We're not going to change it, so this term is right. The next one had 2x times 1/9 e to the 3x, but that one we have now a sign change in it, so we're going to change this to a minus. The next one stays, and if there were more, we just keep flip-flopping the signs. But now I have the right answer. So this demonstrates what we call the tabular or table method of integration by parts. It works really well if you're using u to be the power function like x squared or x cubed, and the other one is something you know its antiderivatives of relatively easily. We're going to try one more example of this where we would need repeated applications of integration by parts, but I'm going to try to walk you through the tabular method this time and just to save a little bit of time. Okay, so I've got the integrand x squared times the sine of 2x, and we're going to try and make this table here to speed up the process of repeated integration by parts. So remember, I'm going to pick u to be x squared and then keep differentiating it until I get to 0. And remember what we pointed out in the first example is we have to account for sign changes, and I'm going to put that in the left margin. Now the dv is going to be this time sine 2x. Now here we have to keep track of not only sines and cosines, but also positives and negatives, because these change signs on their own. So let's think here. Sine is the derivative of negative cosine. So the first antiderivative is going to be negative cosine of 2x. But be careful. This really means we do u substitution here. If this was sine of u, du is 2x. And we'd have to put a 1/2 in this antiderivative. Okay. Now moving forward, we want to find the antiderivative again, which means we're going to be dividing by 2 again. Negative cosine would be the derivative of negative sine. And then we're going to go one more round, which means we have to divide by 2 again. Negative sine is the derivative of positive cosine. Okay. Now, the last example basically demonstrated that if I just multiply every u times every v, I'll have everything I need. And so I'm going to claim here that the answer is x squared times negative 1/2 cosine 2x, and I'm going to write it negative 1/2 x squared cosine 2x. Then the next one, now we have 2 negatives here. There's a negative sign here and here, so those are going to flip it back to a plus. And I'm also going to simplify 2 times 1/4 and put it back to 1/2 x, and then sine 2x. And then finally, we're going to take 2 times 1/8 and make 1/4 cosine 2x. And then that's it. So we go plus c, and this is our antiderivative. Hope this helps. Sorry, it was kind of a long video, but I really wanted to show you that tabular method. It helps really well if your power function like x squared or x cubed is u, and you can find dv easily like this. This makes problems with repeated integration by parts at least a little bit quicker, because you can imagine if the u was x to the 7th, this would be a rather long table, but it would be way worse if you had to do it all out the long way. So this works really nice. I hope this helps you guys, and please keep in touch if you have any questions or just individual problems you're struggling with, and I look forward to seeing you soon.